Hey, all you cool cats and kittens, this is Miss Lemons with the last video of a recorded lesson for the 2020 school year. Crazy. Today we're going to be going over question number 4 on your heat curves or your heating curves worksheet. This question is a doozy. I'm not going to be spending a lot of time going through the nitty-gritty portions like how to do dimensional analysis. Sometimes the setup is present, sometimes it's not. If you need help with dimensional analysis, please view previous videos. So question number 3, I do go over how to do those conversions and do the setups. So let's go on with question number 4. Number 4 says, if 45 grams of water vapor is cooled from 102 degrees Celsius to -6 degrees Celsius, which segments would we pass by and in which direction? So we're starting at 102 degrees Celsius, which is just slightly higher than boiling point, and we're ending at -6 degrees Celsius, which is just below freezing point or melting point. Remember, plateau is melting, this plateau is boiling and condensation. So we're going down condensation, we are going down in energy, down in temperature, so we are moving to the left. So from right to the left, which means we are experiencing an exothermic reaction or an exothermic phase change. So our final answers should have a negative Q value or negative delta T or negative delta H because this is exothermic. Okay, so now we need to calculate the heat energy released or absorbed in joules due to this change. So we are traveling through segments 1 through 5, as you can see here. So we need to be using both Q equals MCAT and Q equals mole delta H of PC, or Q equals moles times the molar heat of the phase change. So we know that for segments 1, 3, and 5, where we have that temperature change, that angle, we're going to be using Q equals MCAT because the at in MCAT is a delta T or a change in temperature, and you can see that temperature is changing in those sections. For sections 1 or segments 2 and 4, we are going to be using Q equals mole times the molar heat of the phase change, and I'll show you guys how to do that in a moment. So let's go ahead and calculate phases or segments 1, 3, and 5 first because it involves Q equals MCAT. This is something we've been using since the beginning of the school year, so it's pretty straightforward for us. Okay, so if we look here, before we do that, there is a slight change. Now, we are familiar with what specific heat is. Remember, specific heat is the amount of energy required to increase the temperature of 1 gram of substance by 1 degree Celsius. If you have a higher specific heat, you require more energy to increase your heat. And depending on the state of matter the substance is in, the specific heat of the substance can also change. So these are values that you will be provided if there is a change in the specific heat. So for instance, we have solid ice or solid water, ice, has a different specific heat than liquid water and vaporized water, which is steam. I went ahead and I provided you with all 3 specific heats, and just because we are moving through all 5 segments of this heat curve, we are going to use all 3 specific heats in different ways. So let's take a look at segment number 1. Segment number 1, we are starting with a value, our T initial for this would actually be 0 degrees. And the reason behind that is because segment 1 doesn't go any higher in temperature than 0 degrees, right? We're not going to say that our T final for segment 1 and only segment 1 is 102 degrees Celsius because segment 1 doesn't get anywhere near 102 degrees Celsius. So our initial, because we're moving from right to left, our initial for segment 1 is going to be 0 degrees. And we know that it's 0 degrees because this right here is our melting point or our freezing point. So we know that by moving right to left to freezing point to 0, our final is going to be the -6 degrees Celsius. So that's why our delta T is being calculated as such. You'll also notice that I picked the specific heat for ice. And the reason is, again, consulting back to your labeled heat curve, you'll see that this section, segment 1 of a heat curve, is always going to be solid. So it wouldn't make sense for us to use the specific heat of liquid water when we're trying to calculate the heat content of solid ice. So we need the specific heat of solid ice. So we're going to go ahead and use 2.090 joules per gram degree Celsius. And again, these types of specific heats will be provided for you. So we simplify the subtraction. Notice that we have -6. We're going to multiply those values together, and we end up with -564.3 joules. Now, I'm not going to round anything right now. I'll just leave the number raw, and I'll come back to it later. Okay, so let's go ahead and calculate for segment 3, another change in temperature. Again, because segment 3 is not going all the way to 102 or all the way down to -6, we have to use the bits that are between the boiling point, this second plateau, and the freezing point or melting point, this first plateau. We know that the melting point or freezing point of water is 0 degrees Celsius, and that the boiling point or condensation point is 100 degrees Celsius. So because we're moving from right to left on our heat curve, our initial temperature is going to be at the top of section 3, so it'd be 100 degrees Celsius. So T initial is 100, and T final will be 0. So that's T final minus T initial, giving us -100 degrees Celsius. You'll also notice that my specific heat is back to quote unquote normal, but that normal is the specific heat for specifically liquid water. So we have to use liquid water because we know that substances that are in segment 3 are in fact liquid. Multiply those values together and we end up with -18,828 joules. The last segment is segment 5, and just like we've done before, because segment 5 doesn't go all the way down to -6 degrees Celsius, we have to use which parts of it are actually present in up here. We can't use the stuff down here. So because we're moving right to left, our initial is going to be the highest value given to us, so 102 degrees Celsius. And then remember, we're warming, or we're cooling it down, so we're moving to the left. And so segment 5 stops right here at the boiling point or the condensation point of water, which happens to be 100 degrees Celsius. So T initial T final is 100 degrees Celsius minus T initial, which is 102 degrees Celsius. And then again, because we're in segment 5, we know that all substances that are in this rightmost segment, segment 5, they are completely gaseous. So we want to be using the specific heat for steam, which is vaporized liquid water, right? Vaporized water. So we're going to plug that specific heat value in for C instead of the liquid water one. Plug that in and simplify our parentheses. We get -2 degrees Celsius for our delta T. Multiply them all together, and we get -182.7 joules. So those 3 values, I'm going to go ahead and just put in my back pocket and save them for later. Write them off to the side. Make sure you have all of this work, and keep it this organized too when you guys are walking through these types of problems. Putting a box around your work, or labeling in different colors, or keeping your labels really clear is going to help you with these types of questions. Okay, so now that we've done segments 1, 3, and 5, we have to take a look at the other segments, 2 and 4. We need to calculate the heat energy released in segments 2 and 4. And remember, those segments are going to be using our new formula, the Q equals mole delta H of the PC. So moles times the molar heat of the phase change. That's what PC stands for. But unfortunately, it's asking us for moles, not grams. So we need to convert mole or grams of water into moles of water. And we're going to be using this conversion factor. Now, I'm not going to sit here and walk through how we set this up, but I've gone ahead and shown you what the setup looks like. If you do need help with that setup, please watch video 3 or question 3 video. So our final moles after the conversion is 2.4972 moles of H2O. So I just converted grams to moles so that I can put it into this equation. And remember, this is why it's important to have units on everything. So now we're going to go ahead and plug this value in for moles and solve for segments 2 and 4. Now, you'll notice over here on the right-hand side, I have a list of molar heats of phase changes, and you will always be provided with these just like you would be provided with specific heats at different phases. So it's up to us to determine which values we are going to plug into the equation for us to use. And it's totally dependent on two things. Which segment are you in and what direction you are moving? So we are in segment 2. And remember, we are cooling down. So we are decreasing the amount of heat energy. So we are moving from right to left. We are losing energy. And if we're losing energy, energy is exiting the system. And if it's exiting the system, it's exothermic. And we know that exothermic reactions have a negative delta H. Cool. So if we take a look at our molar heats of phase changes for solidification, fusion, condensation, and vaporization, you can see that 2 of the 4 of them are negative. And that's because 2 of the 4 of those processes are exothermic. Now we need to determine which one of those 2 negative values am I going to use. So this is where you need to know your vocabulary. We're moving from left or from right to left, and we're going from liquid to solid. Normally, we would call this freezing, but we don't have a molar heat of freezing. The synonym to freezing is solidification, to become solid. So we would want to use the molar heat of solidification, which is negative 6.01 kilojoules per mole. So that's why I plugged negative 6.01 kilojoules per mole in that spot. Go ahead and throw that into your calculator and multiply them together. We end up getting negative 15.008 kilojoules. Okay, so now, and by the way, folks, I know that this is going to be in kilojoules too because I have kilojoules in my measurement here. It is possible for you to receive molar heats that have joules in them. And if they do have joules, your final answer for Q would then be in joules. All right, we're going to do the same thing for segment 4. Again, we're moving from right to left. And so we're decreasing the amount of energy, which means it's exothermic. So it's still exothermic. It's the same type of phase. It's the same scenario. And we know we're going to be looking for a negative delta H value. Well, we already used the molar heat of solidification. So logic by process of elimination tells us that we have the molar heat of condensation. And this makes sense because to condense something means to take a gas and make it a liquid, right? Those particles are losing energy, they're moving less, they're starting to become more attracted to each other and therefore start creating that liquid. So, or forming that liquid. So we are going to be using negative 40.7 because that is the molar heat of condensation. Plug that into our calculator and we end up with negative 101.64 kilojoules. So I'm going to take those two values, put those in my back pocket, and we're going to go ahead and wrap up this question. Now, the best part of this, we just have to add up segments 1, 2, 3, 4, and 5. But we have to be really careful. We need to make sure that all of our units are the same. You can multiply things that aren't the same unit, but you cannot add or subtract things that aren't the same unit. So they need to be the same. Take a look at this. It's asking us for the answer in joules. So we need to convert segment 2 as well as segment 4 in order for us to successfully add all of these values together. I'm not going to spend time going through how to do those conversions, so I've already done them for you. Notice that all of our values are also negative, which makes sense because we are cooling down, losing energy. And so every segment of the graph should be negative. Once we've converted everything to joules, we'll go ahead and add those values together. Now, notice the way I put parentheses around every negative value. I highly recommend that you do the same in your own calculator. This is so you can avoid any errors with order of operations. It's also important to know that when you have your calculator out, that you're not putting negative symbols in with this button here. That button is the function of subtraction. We don't want to use subtraction. We want a negative symbol. So make sure that you are pressing this button here. It's a pretty small little negative symbol. And you'll see the difference here. When I press the negative symbol, -3, we actually create a -3. Whereas if I were to do it with the minus symbol, it thinks we're subtracting from the current answer. So you're not going to be able to get that negative sign. So be careful with that when you are calculating in your calculator. So once we've added all of those values together with the negative symbols included, we end up with the final answer of negative 1,036,223 joules. We need a round according to the rules of sig figs. Our lowest number of sig figs is 2 sig figs. So we underline our top 2 placeholders and round up. So our final answer is negative 140,000 joules of heat released. So this we know is correct because we are cooling down, so we are losing energy. So our final answer, that Q value, that delta H value, it should be negative. Again, if you guys have any questions or need me to walk through any of these other problems, again, either review those videos or reach out to me and I can get you some extra practice problems. Thanks and good luck.